Assalamu alaikum, everyone. I'm Golam Ishtiak. I'm currently doing bachelor's in physics in Nanyang Technological University, Singapore. And আজকে আমরা ডিসকাস করব গ্র্যাভিটি নিয়ে। সো গ্র্যাভিটি নিয়ে বলার তেমন কিছু নাই, আসলে সবাই গ্র্যাভিটির ইউজফুলনেস কি সেটা মোরাললেস জানি। দিস ওয়াজ ওয়ান অফ দ্য ফার্স্ট ইউনিভার্সাল ফিজিক্যাল লস, যেগুলো একটা ক্লোজড ফর্মে আনা হয়েছিল বাই নিউটন। সো আমরা অ্যাকচুয়ালি নিউটনিয়ান গ্র্যাভিটি পড়বো মেনলি। সো নিউটনিয়ান গ্র্যাভিটি দিয়ে যদি আমরা স্টার্ট করতে যাই, we obviously encountered the Newton's gravitational force law first, which tells you that the force between two objects is g m1 m2 divided by r squared. এখানে আরো কিছু ভেক্টর সাইন দিয়েছি, we will get into that now. So 1 2, so let's say we have two objects. এটা হচ্ছে object 1, have another object that is object 2, and then either মধ্যে distance, the distance between them is r12. Mass of the first object is m1, mass of the second object is m2. Okay, so এদের মধ্যে একটা ফোর্স থাকবে। Gravitational force is always attractive. I hope most of you guys know this because এটা usually আমাদের কারিকুলামে দেখা যায় ক্লাস 7 ডিসকাস করা হয়. So I will go a bit fast through this. This is always attractive. So এই দুইটা অবজেক্ট এদের ম্যাসের কারণে একটা ফোর্স ফিল করবে, that force will be attractive and they will be equal in opposite in magnitude. কেন? Because of Newton's third law. So by Newton's third law, we already know that F12 is equal to minus F21. All right, so what is the value of this force? This force will be the value of this force. So if we instead write it like this, modulus of F will be G m1 m2 divided by r12 squared. m1 m2 হচ্ছে their mass, so mass এর proportional, r12 এদের মধ্যবর্তী distance, so distance এর inverse square এর সাথে proportional, and this proportionality constant is g. This is called the gravitational constant, universal gravitational constant, and এর value হচ্ছে 6.673 into 10 to the power minus 11. And the units should be Newton meter square per kg square. You can try to substitute in Newton to get it in terms of SI units as well. Okay, so this is how you get the force between two objects. But this is not the force between any two objects. There are some other underlying assumptions. First, let's say m1, m2 both are point mass. Point mass মানে কি? They are very small. They are basically points in space. Now, that is very restricting because obviously আমরা points নিয়ে কাজ করি না. In fact, real life আমরা point identify করতে পারি না. Everything we see in real life are extended objects. But then if these were not point masses, then question আসতে হচ্ছে what is R12? If they are points, if they are small points, এদের মধ্যে distance বের করা নিয়ে কোনো ambiguity নেই. It's just একটা থেকে আরেকটা distance. But if they are extended objects, so এটা যদি আমার object 1 হইতো, এটা যদি object 2 হইতো, then even if you consider that this equation is correct, which is not by the way, then question arises just what do I take for R12? What is the distance between these two objects? And the answer is there is no certain way to calculate distance here. If you take different points, you get different distances. So this law is only applicable to point mass. But wait, so I'm not always point mass নিয়ে কাজ করব না. What do we do if we don't have a point mass? What if we have a extended object? The general approach is to integrate this force over all the points. Because if you have an extended object, let's say you have a rod, you can consider that this rod is made up of a lot of point masses. And then you can integrate to find the net force over all of them. But then integration is not part of our curriculum right now. We won't be discussing that. So our study will be restricted by point mass and some specific symmetric scenarios. So first আমরা point mass-এর কিছু example দেখব. Point mass-এর বাইরে we will just learn another case যেটা integration বাদে করা যায়. That is for sphere or spherical shells. And then we will move on to discussing orbits and trajectory of objects under gravity. Okay, so point mass actually আমাদের discussion হয়ে গেছে. Another thing to notice is obviously this is a force. Forces are vectors. So whenever you try to find force on some object due to different particles, you have to do a vector addition. The usual superposition principle still holds. So if we, let's say, have 3 particles, this is one, okay, this is object 1, this is object 2, this is object 3. So the net force on object 1 will be force due to object 2. So we assume object 3 নাই, just object 2 যে পরিমাণ force দিবে সেটা. Then we assume the other case that object 2 নাই, just 3 আছে, এখানে একটা force দিবে. Then এই দুইটার vector sum করলে যেটা আসবে, that will be the net force. That is basically superposition principle, and you can apply superposition principle here. Basically, you assume just একটা particle আছে বাকিগুলো নাই. You find out the force. In that case, you can use this formula. You can do the same for all other particles. And প্রত্যেকটা জন্য তুমি individually force কত হবে পেয়েছো, and সেই সবগুলো force যদি তুমি vector sum করো, you will get the net force. All right, so let's do a quick example. এটা অনেকটা একটা common example এর মতনই হবে. This is a very common example actually, but in electrostatics. So let's say we have 2 objects. একটার mass হচ্ছে 10 kg, আরেকটার mass হচ্ছে 30 kg. And the distance between them is, let's say, 100 meters. And then I want to place a new object on this line so that that object doesn't experience any net force. So I want to position another object here so that that doesn't experience any net force. This is actually easier than the electrostatic case because তোমার এখানে positive negative mass এর কোনো ঝামেলা নেই. Mass is always positive. So the force you have is always attractive. You cannot place it here because এখানে place করলে both of your forces are pointing in this direction. দুইটাই attractive যেহেতু. So your net forces cannot cancel. It cannot be on this side either because in that case, both of your forces point in this direction. So the net forces cannot cancel. If your object is somewhere in the middle, then a force দিবে এই পাশে and the 10 kg will give the force in this direction. So your forces can cancel. So just we assume that this distance is x. If that is x, this distance will be 100 minus x. Then we just find the forces. We assume air mass would say m, which will end up canceling out, so that doesn't matter. Prothom force F1, let's call this F1, and let's call this F2. So F1 will be G, we're just working with the values, no directions. G times 10 times m divided by x squared. Similarly, F2 will be G times 30 times m divided by 100 minus x squared. And then at equilibrium, যেহেতু the question asks us to find the point যেখানে কোনো force অনুভব করবে না, we basically set them equal to each other. So we set this equal to this. M, M, G, G cancels out. You have a 3. So ultimately, what you get is 100 minus x whole squared is equal to 3x squared. If you expand this, you'll get 2 solutions for x, but you only take the positive one because the negative one will give you a solution যেখানে ফোর্সের ভ্যালুগুলো সমান, but the directions won't be different. Directions will be the same, so the forces will add up. So we only take the positive value since it makes sense in this case. If you just expand this, you will get something like this. You'll get 2x squared plus 200x minus 10,000 is equal to 0. Right? You get x squared, it goes to that side, 2 cancels out. You have negative 200x, positive 200x. Yes. Then if you solve this equation, you'll get a positive solution and a negative solution. You only take the positive solution because that is the one that is physically consistent. Okay, you guys have also learned vectors. So if I had given a question like this instead, let's say I have an object here that is 10 kg, another object here, which is, let's say for simplicity, also 10 kg. And these distances are 10 meters each. So both of these are 10 meters each. All right, and then there is another object here, which is at height 20 meters. And air mass হচ্ছে 5 kg. We want to know the net force on the 5 kg object. Let's mark this. This is 1, this is 2, this is 3. We want to know the net force on object 3. Well, we do the usual. Basically, 10 kg জন্য লেফটের 10 kg জন্য একটা force থাকবে that will be along this line. So this will be the force due to 10 kg object. And right at 10 kg objecটের জন্য যে force থাকবে that will again be along the connecting line. So that will be along this line. And as you can see from symmetry, these two forces will have equal magnitudes. কেন? Because distance same, mass same. The distance between these two, so R23, you can clearly see which is this hypotenuse, that will be square root of 20 squared plus 10 squared. And same for R13. It's just the opposite side, base still 10 and the perpendicular is still 20. If this value was different, you just similarly just apply Pythagorean theorem and you get a different value. But in this case, they're the same. So if you do this, I think you would get something like 10 root 5 meters. So this will be my distance. So what about the magnitude of the forces? We'll get F13 is equal to F23, and that is equal to G times 10 times 5 divided by 10 root 5 whole squared. So if we simplify this a bit, 5 katakati jai, we get G over 10, I think. Yeah, you get G over 10. So G over 10 is the force on both sides. So this is also G over 10. This is also G over 10. But then we're not done. We still have to add these two vectors vectorially because we are asked for the net force. And remember, we're adding forces. So you have to do vector addition. So vector addition is when actually we need to know this angle. Oops. We need to know this angle and this angle. But coincidentally, again, due to symmetry, these two angles are equal. So eta theta hole eta theta. Because again, base is 20. Sorry, base is 10. Perpendicular is 20. So those two angles are supposed to be the same. And what is the value of those two angles? যদি ট্রায়াঙ্গেলটা এখানে টেনে আনি, this is 10, this is 20, this is a 90 degree, and then this is theta. And we even know that this is 10 root 5. So we can write that theta is tangent inverse 10 over 20, which is basically tangent inverse of half. Or if you don't like tangent, you can use cosine or sine. If you can also use sine inverse would look nice, I guess. Sine inverse করলে perpendicular by hypotenuse. So there will be 10 divided by 10 root 5, giving you sine inverse 1 over root 5. These two values are the same. তুমি ক্যালকুলেটরে বসে দেখতে পারো. These two will give you the same value of theta. Okay, so it doesn't matter whichever you use, you can plug it into calculator, you'll get a value. But then we now have to add two vectors. আমি যদি এই ভেক্টরের সিনারিওটা এখানে তুলে আনি, then we basically have a scenario like this. This is g over 10. This is g over 10. And the angle here is 2 theta. You can use different methods to find the sum. The easiest one will be by components. You can clearly see here যে আমি যদি এই দিক বরাবর একটা কম্পোনেন্ট নিই, both will cancel out because এর দিক বরাবর কম্পোনেন্ট হচ্ছে g over 10, the value of the force, times sin theta, which is pointing to the right. And এই দিকের কম্পোনেন্ট হচ্ছে same, g over 10 sin theta, but it's pointing to the left. So this and this cancels out. But the vertical components add up. এর vertical component হচ্ছে এখানে, এরও vertical component same direction. So those two just add up. So my net force, the sum of these two force vectors, will just be g over 10, the value of the force, cos theta, plus g over 10 cos theta, which is basically g over 5 cosine theta. What is cosine theta? এই triangle থেকে দেখো আমরা cosine theta বের করে ফেলতে পারবো. Cosine theta will be আমার g over 5 এরকম থাকবে. Cosine theta will be 20 divided by 10 root 5. So we can cancel some things out. এখানে একটা 2 থাকবে. So my net force becomes 2g divided by 5 root 5. And the direction is along negative j cap because it's pointing directly towards the negative z axis. So this will be my net force. If you don't want this, you can now also use the Pythagorean theorem, not the Pythagorean theorem, the parallelogram theorem to add the two vectors you have here. Basically, it doesn't matter which method you use. If you use it correctly, you should get the same net force. All right, so that was our discussion about point masses. So point mass থাকলে কি করতে হবে? Just to sum things up, you find the force due to each point mass and then add them vectorially. Vectorially is an important concept because vectorially add na korle you'll get wrong answers. Even if it's one dimension, you need to account for plus and minus signs. And if it's in two dimensions, you need to work on components. X component একটা থাকবে, Y component একটা থাকবে. You need to do those calculations separately. Okay. All right. So the next thing we will discuss is for sphere. Or not actually sphere, spherical shells. And এটাও করতে আমাদের ক্যালকুলাস লাগার কথা. We would have needed integration, but instead of using integration, we will use two theorems that Newton proved basically with calculus. We won't be proving those. We will just take those theorems as granted and then use those to find the answer. So এগুলা হচ্ছে the first one is called the first shell theorem. These are called Newton's shell theorem. There are actually 3 shell theorems, but we will only learn 2. The first 2. The third one is for elliptical objects, so we won't be getting into those. Okay, so what does the first shell theorem tell? The first shell theorem tells you that if you have a spherical shell, what do I mean by shell? Shell মানে হচ্ছে ভেতরে ফাঁপা, ভেতরে কিছু নাই. So the inside is empty. And আরেকটা কি? Mass uniformly distributed. So when I say shell, it's empty and mass is uniformly distributed along the outer surface আর কি. This is the only surface it has. ভেতরে ফাঁপা. So এই সারফেসের উপর যে mass সেটা uniformly distributed. So this is the setup you have for both the first and the second shell theorem. You have a spherical shell যার mass density হচ্ছে uniform, mass uniformly distributed. Okay, so the first theorem tells you that if you have such a structure, net force on any particle inside the shell due to the shell is 0. সো এই শেলটা কি করবে, যে কোনো অবজেক্ট তুমি যদি এখানে একটা পার্টিকেল দেখো এর সাথে গ্র্যাভিটেশনালি ইন্টারঅ্যাক্ট করবে, এই শেলের প্রত্যেকটা পয়েন্ট থেকে অ্যাট্রাক্ট করবে, প্রত্যেকটা পয়েন্ট এভাবে একে অ্যাট্রাক্ট করবে। এন্ড আমরা কি বলতেছি যে ইফ the mass of the shell is uniformly distributed, if the mass of the shell is uniformly distributed, then the net force on a particle inside the shell is always 0. Inside the important word, because if you go outside then it's a different case. Outside it actually second shell theorem, but as long as you are inside the shell, the net force due to the shell is 0. এখানে আরেকটা পার্টিকেল থাকতে পারে, সে এর সাথে ইন্টারঅ্যাক্ট করতে পারে, বাট জাস্ট শেলের জন্য যে ফোর্স থাকবে দ্যাট উইল বি 0. So just to sum up one more time, what do you have to apply the shell theorems? You need to have a spherical shell that is empty inside and the mass is uniformly distributed on the edge. For such shells, if you have any object inside the shell, শেলের জন্য ওই অবজেক্টের উপর net gravitational force is 0. You can like get a general idea of why this happens, because এরা দেখো ফোর্স দিতেছে বেশি because these are close, but ক্লোজে থাকা পার্টিকেলের সংখ্যা কম, এগুলো আবার দূরে আছে, so ফোর্স কম এদের জন্য, since the force is inversely proportional to the distance, but এদের জন্য দেখা হচ্ছে পার্টিকেল বেশি. So you can, like, if you know integration, you can rigorously show that these two effects cancel out and the net force is always 0. Okay, so what about the second shell theorem? Second shell theorem idea same. You have a spherical shell that is empty inside and the mass is uniformly distributed, but now your particle is outside. So the net force on any particle outside the shell due to the shell. আমরা again just শেলের জন্য gravitational interaction হিসাব করতেছি, not for anything else. Shell is as if all of its mass is concentrated at its center. Basically, this is telling you that if your particle is outside the shell, then the shell behaves like a point particle. So here's my shell. Again, the conditions are mass uniformly distributed. And then we say এর radius হচ্ছে r, এর mass হচ্ছে m, and then we have this particle that is out here, which is, let's say, center থেকে distance হচ্ছে ছোট হাতের r, এর mass হচ্ছে ছোট হাতের m. If you want to find the total force on this object, what do we do? Second shell theorem tells us that this is equivalent to the case where all of the shell's mass is concentrated at its center. So শেলের সব mass concentrated থাকবে হচ্ছে এর সেন্টারে. And here is your object here that has mass m, and this distance is r. In a case, we know how to find the force. It's just 2-point particles. So the total force is just gmm divided by r squared. R being center থেকে distance. কেন center থেকে distance? Because all of his mass is concentrated at his center. So when আমরা এই ইউনিফর্ম শেলটার বাইরে আছি, তখন শেলটা কিভাবে বিহেভ করে? যেন এর সব ম্যাস এর কেন্দ্রে কেন্দ্রীভূত আছে। আসলেই কি আছে? Obviously না, this is a shell, mass distributed আছে. But for gravitational purposes, it behaves as if all of its mass was concentrated at its center. Okay, so that helps us solve problems like this. Let's say we have two spherical shells. A radius হচ্ছে 2r, A radius হচ্ছে r, and the edge to edge distance, A distance, is, let's say, L. এর mass হচ্ছে 2m, এর mass হচ্ছে m. And then I want to know what is the force between them. So আমি কি করতে যাচ্ছি? এই শেলের, oh, by the way, the mass is uniformly distributed for both objects. Okay, so mass uniformly distributed. তাহলে যখন আমি এই শেলটা নিয়ে কাজ করতেছি, এর বাইরে একটা পয়েন্টে আমি ফিল্ড বের করতে যাচ্ছি, I will treat it as if all of his mass was concentrated at his center. So 2m mass is center concentrated. এরও আমি বাইরে বের করতে যাচ্ছি, সো এটারও আমি এমন ভাবে ট্রিট করবো যেন এর সম্পূর্ণ ম্যাস এর সেন্টারে কনসেন্ট্রেটেড। সো এই সেন্টার টু সেন্টার ডিস্টেন্স তাহলে আমার এখন নেওয়া লাগবে টু ফাইন্ড দ্য ডিস্টেন্স বিটুইন 2 পয়েন্ট পার্টিকলস। নোট, আমি কিন্তু স্ফিয়ার গুলোর মধ্যে ফোর্স বের করতে পারি না, বাট আই ডু নো দিস ইজ যে when I am outside the sphere behaves as if all of its mass was concentrated at its center. সেই জন্য যখন আমি এই GMM by r square ইউজ করতে যাব, the r I have to use will be center to center distance. And the center to center distance in this case will be L plus 3r. 2r from here and 1r from here. So my total force will be G times 2m times m divided by L plus 3r whole squared. Okay, so এখানে আরেকটা এক্সাম্পল গেল, বাট হোয়াট ইফ আই হ্যাভ spheres instead of shells? আমরা এতক্ষণ যা কাজ করলাম, we are working with shells, not spheres. Both of our shell theorem, they are called shell theorem because they work on only shells, not full spheres. So we will be doing a very common problem. আমাদের কাছে একটা r রেডিয়াসের sphere আছে. So this is a sphere. Of uniform mass density. So the density হচ্ছে same, constant density, and the radius হচ্ছে r. To start off, we want to find যে সেন্টার থেকে r ডিস্টেন্সে what is the force on an object of mass m? ও এর টোটাল মাস হচ্ছে m, বাই দ্য ওয়ে। স্ফিয়ারের টোটাল মাস হচ্ছে m, অ্যান্ড এর সেন্টার থেকে r ডিস্টেন্সে আমরা ফোর্স বের করতে যাচ্ছি। So we want to find the force as a function of r. This will actually be a piecewise function. First case, which is more trivial, that will be when r is greater than or equal to radius r. So when the particle we're looking for is outside the sphere. And the other case will be when this is not. So আমরা বেসিক্যালি দুইটা ফোর্স বের করবো এখন, দুইটা ইকুয়েশন। They might turn out to be the same, they might not turn out to be the same, we don't know. But we are just assuming there might be two cases here. So এই দুইটা ইকুয়েশন আমাদেরকে বের করতে হবে। So let's first consider the easier case. যখন আমাদের particle, the mass m, is outside the sphere. এটার জন্য what do we do? The key idea to deal with spheres is that, remember, spheres are basically made of spherical shells. Not are, can be made of. So basically আমরা একটা শেলের উপর আরেকটা শেল স্ট্যাক করে 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 we can make a sphere. So instead of considering this as a sphere, we will consider this as a lot of uniform shells. এরকম অনেকগুলো শেল আছে যেগুলো একটার উপর একটা চাপা দিয়ে 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 you make the sphere. Okay, so if that is the case, then দেখো, for each shell আমার এখানে I will have infinitely many shells, but প্রত্যেকটা শেলের জন্যই my mass is outside the shell. The largest shell I will have is this one, the outermost one. So even for the outermost one, the point of constant is outside the shell. So if it's outside the shell, then how do we find it? We go to the second shell theorem. Second shell theorem অনুযায়ী এর ভেতরে যতগুলা শেল আছে, for all of the shells inside, they will behave as if all of their mass was concentrated at the center. And coincidentally, the center is common. সবার center point same. So an equivalent problem, gravitational equivalent problem, is you have a particle, you have a point, যেখানে total mass m centered আছে. Here is your point r, here is your object m, which is now at a distance r. This is now your equivalent problem. And এখানে আমরা জানি কেমনে ফোর্স বের করতে হয়. It's just the first equation, gmm divided by r squared. This r is কি? এটা আবার center to object এর মধ্যে distance, which is very simple. Why did it turn out to be so simple? Because আমার যতগুলা শেল আছে, my object is outside all of those shells. So what ends up happening is সবগুলা শেলের ম্যাস যখন সেন্টারে কেন্দ্রীভূত আছে আমরা ধরি, সবগুলা শেলের সেন্টার সেম, because they are concentric shells. So what ends up happening is পুরা ম্যাস একটা পয়েন্টে কনসেন্ট্রেটেড হয়ে যায়, which is the center of the sphere. So here the first equation we get is just our good old gmm divided by r squared. ঝামেলা হচ্ছে পরেরটা. What happens when your object is now inside the sphere? This is a very common problem, as in আমরা আর্থের জন্য নরমালি এটা এরকম প্রবলেম সলভ করে থাকি যে আর্থের সারফেস থেকে সারফেসের উপরে থাকলে গ্র্যাভিটেশনাল ফোর্স কেমন হবে, সারফেসের নিচে থাকলে কেমন হবে, and so on. By the way, one more thing I should probably discuss, because আর্থের কেস যখন আমি বলেই দিলাম, আর্থের কেসে আমরা ইউজুয়ালি ফোর্সের থেকে we work with field. This force can be written as m times g, which is called the gravitational field. Also sometimes called gravitational acceleration. because this has the same units as acceleration. And if you solve for it, your G just becomes gm divided by r squared. So you basically assume that this m is equal to 1. Then the force will basically be the gravitational field. Since we have introduced gravitational field, I will just turn this into a gravitational gravitational field problem instead of force problem. Because force বের করতে you need to know, like, you have a very specific mass here যার জন্য you find the force. But if you find the gravitational field, then force পাওয়া কোনো issue না. You just এখানে whatever mass you have, you just multiply it with the field and you get the force. If you use the force, then এই massটা কাটাকাটি চলে যাবে. And as you can see, আমার gravitational field আর gravitational forceর মধ্যে difference হচ্ছে just একটা massের. So they behave exactly the same way. Force যেভাবে add হয়, gravitational fieldও সেভাবে add হয়, superposition principle মানে, and so on. Okay, now we go to the second case. যেখানে we have a planet of radius r, not r. Actually, I'll just write it here. Planeটের radius হচ্ছে r, mass হচ্ছে m, uniformly distributed. Okay, and then আমার সেন্টার থেকে ছোট হাতের r ডিস্টেন্সে আমার গ্র্যাভিটেশনাল ফিল্ড জানা লাগবে। But this ছোট হাতের r is now smaller than the radius. Okay, so এখন আমার যে পয়েন্টে আমি গ্র্যাভিটেশনাল ফিল্ড বের করতে যাচ্ছি, that is inside my sphere. So remember, আমরা কিন্তু জাস্ট শেল থিওরেম শিখছি। আমরা এখন সেই শেল থিওরেম অ্যাপ্লাই করতেছি ফর solid spheres. Okay, let me do a quick check first. Okay. Alright, so আমরা যদি সিমিলারলি এটা আবার চিন্তা করতে থাকি, মেন আইডিয়া কি? মেন আইডিয়া হচ্ছে the spheres we work with, they are basically made of they are basically made by stacking spherical shells one on other. একটার উপর একটা শেল লাগায় we make the whole sphere. So এই কেসে what changes is if we consider a shell around this, এই শেলের ভেতরে যে পয়েন্টগুলো আছে, এই শেলের ভেতরে যে শেলগুলো আছে, আর এই বাউন্ডারির ভেতরে যে শেলগুলো আছে, তাদের জন্য আমার পয়েন্ট হচ্ছে এক্সটার্নাল, সো দে অ্যাপ্লাই সাম নেট ফোর্স। বাট আউটসাইড যে শেলগুলো আছে, এখানে যে শেলগুলো আছে, ফর এক্সাম্পল, দে ডোন্ট এক্সার্ট এনি ফোর্স অন দিস পয়েন্ট। ওয়াই? নিউটনস ফার্স্ট শেল থিওরেম। ফার্স্ট শেল থিওরেম কি বলে? যে ইফ ইউর পয়েন্ট ইজ ইনসাইড দ্য শেল, দেন ইউ ডোন্ট হ্যাভ এনি নেট ফোর্স, and this point is actually inside the shell. তুমি যদি এই বাইরের একটা শেল নাও, if we take, আচ্ছা, not green, let's take blue. If we take this shell, the point of concern is inside the shell, so it applies no net force. So we can basically forget about the points outside. বাইরে যে পয়েন্টগুলো আছে সেগুলোর কথা আমরা কমপ্লিটলি ভুলে যেতে পারি, সেগুলো আমাদের আর চিন্তার দরকার নেই, বিকজ by Newton's first shell theorem they don't exert any net force. So we just need to find the net force exerted by this part, this sphere. But wait, this is the same problem we had before, just আমার রেডিয়াসটা চেঞ্জ হয়ে গেছে। আমরা বাইরের অংশটুকু ভুলে গেলাম, আমার জাস্ট রেডিয়াসটা চেঞ্জ হয়ে গেছে, এইটুকুর জন্য কতটুকু ফোর্স দিবে। So naively you might think that my new force will just be gmm, acha, new field, we're working with fields, not force anymore, will be gmm by r squared, which would be correct if not for the fact that my m has also changed. Because remember what m is. This is wrong, by the way. So let me just point it out so it doesn't confuse anyone. Okay, remember what m is. M is mass of the whole thing. But we don't need mass of the whole thing. We just need mass of this part. How do we find mass of this part? Well, remember we have uniform density. So it's not a big deal to find the mass of this part. Let's find the density first. Density is m over v, which will be total mass divided by total volume, which is 4 pi r cube by 3, which comes on the top. So this is my density. So the mass inside this part, if we call it m prime will be rho times the volume of that part, which is 4 by 3 pi choto hater r cube, since the radius is choto hater r. Plug this back in, you have 3m divided by 4 pi r cubed times 4 by 3 pi r cubed, 4 pi pi, 3 katakati. You are left with m times r cubed divided by r cubed. So this is my new mass. So my new field will be g m prime divided by r squared. Let's substitute m prime. You have g m r cubed divided by r cubed times r squared. So একটা r কাটাকাটি যায়, you were left with gm by r cubed times r. So this is the gravitational field inside Earth. So if we plug this back in, we are done with the derivation. This will be gm by r squared, r by r. So Earthের বাইরে গেলে you just use the usual formula gmm by r squared. But whenever you go inside the Earth, your formula changes to this. Which makes sense because if you plug in r is equal to 0, if r is equal to 0, that gives you g is equal to 0. So at the center of the Earth, there is no gravitational field. There is no gravitational force. Because remember, my force is just m times g. So if your g is 0, your f is also 0. You can also take another boundary case that if r is equal to r, so if you are at exactly the surface, your g becomes gm by r squared. And that is the same for this case as well. If r is equal to r, g is equal to gm by r squared. As expected, you don't want a like sudden jump in gravitational field. Real life and most of the values we see are continuous, and we expect g to be continuous around this surface as well. And as you can clearly see, তোমার উপরেও gmm by r square আসবে, নিচে যদি তুমি r is equal to r বসায় দাও, you will get gmm by r square. Okay, so that's about it for gravitational fields and forces. I guess I will just briefly discuss the third shell theorem. The third shell theorem is actually for an elliptical object. So if you have an elliptical shell, again, what does it have to be? It has to be elliptical. Elliptical shell. Shell means bhetore ফাঁপা. And also mass uniformly distributed. So if you have an elliptical shell with uniform mass distribution, the net force inside the shell is 0. So if you place an object inside the shell, anywhere inside the shell, as long as it's inside the shell, net force inside is 0. Inside the shell due to the shell. So is 0. This is called the third shell theorem. Is there a fourth shell theorem যেটা ডিসকাস করবে যে আচ্ছা আমার ইলিপ্টিক্যাল শেলের বাইরে থাকলে কি হবে? No, there is actually no fourth shell theorem. In fact, the only way to find the net force due to an elliptical object outside the ellipse or outside the ellipsoid is to do integration. So there is no fourth shell theorem. Third is where it ends. You will probably never need the third shell theorem, but first and second shell theorem, you should need to use it consistently for different problems, especially problems like this, finding the gravitational field like at a certain depth from Earth's surface and so on. Okay, so the last thing we will discuss today is orbits under gravity. And this is actually a large topic as well. So what we will start with is we need to know about centripetal force. So whenever an object moves in a circle, remember আমার যে কোনো অবজেক্টের let's say velocity constant, not velocity, it's speed constant. So it's moving at speed v. So speed constant হলো এর velocity কিন্তু চেঞ্জ হইতেছে, এর velocity direction দেখো consistently চেঞ্জ হইতেছে. That means it must have a acceleration. Because acceleration is velocity change rate. Even though speed change হইতেছে না, direction change হইতেছে, which in turn makes the velocity change. That means there needs to be a force on this object. There needs to be acceleration. Acceleration কোথা থেকে আসবে? Acceleration আসবে force থেকে. So there must be a force on this object. That force is called the centripetal force that is directed towards the center, and এর value হচ্ছে mv squared over r, where r is the radius of the trajectory. Okay, so আর রেডিয়াসের একটা সার্কুলার ট্র্যাকে যদি স্পিড ভিতে ঘুরতে হয় কোনো একটা অবজেক্টে, এর ম্যাস যদি এম হয়, এটার জন্য এর সেন্টার বরাবর একটা ফোর্স থাকা লাগবে। ইটস নট দ্যাট আ ফোর্স কাজ করছে, দিস ইজ আ ফোর্স দ্যাট ইজ রিকোয়ার্ড যেন এস এরকম একটা সার্কুলার ট্র্যাকে ঘুরতে পারে। is as you can see acceleration থাকা লাগবে, so it has to have acceleration towards the center of v squared over r. এই পরিমাণ acceleration পাওয়ার জন্য the required force will be mv squared over r. Okay, so all right, so planetary motion এর জন্য we will basically look into Kepler's 3 laws. Kepler তিনটা law অনেকগুলো ভার্সন আছে, but we will learn the first version that Kepler himself found, that is for circular orbits. Circular orbits actually circular এর বাইরে elliptical হইতে পারে, and then other unbounded objects can be parabolic or hyperbolic, but we won't be getting into those. We will be just dealing with circular orbits. So for circular orbits, we have Kepler's first law. এটা কি বলে? এটা বলেছিল হচ্ছে যে all the planets in the solar system orbit in circular orbits with the sun at the center. So basically এটাকে যদি আমরা একটু জেনারেলাইজ করি সোলার সিস্টেমের বাইরে, দেন বেসিক্যালি একটা ম্যাসিভ অবজেক্ট থাকবে which is স্টার, যেটা সেন্টারে থাকবে, and এটাকে সেন্টার করে বাকি সবাই সার্কুলার ট্র্যাকে ঘুরবে। Or even generalize করলে we can basically write the most general version that all objects move around in circular tracks around the center of mass of their, or around their common center of mass basically. Now what is center of mass? সেন্টার অফ মাস আমাদের সবারই মোরালেস আইডিয়া থাকা উচিত। It's basically defined like this. This is sum of MIRI divided by all M. So নিচে একটা summation of M. So for example, let's say I have, this is my sun, যার mass হচ্ছে ms. This is earth, যার mass হচ্ছে me. এদের মধ্যে distance ধরলাম বড় হাতের r. So if I want to find the center of mass, first I have to establish a coordinate system. Let's take sun's center to be our coordinate system center. Then I first have to evaluate the sum above. উপরের সামে আমার দুইটা ম্যাস আছে, সো দুইবার সাম হবে। একবার হবে ms সানের ম্যাস টাইমস সানের পজিশন। সানের পজিশন ইজ 0 জাস্ট বিকজ সান 0 0 তে আছে, প্লাস আর্থের ম্যাস টাইমস আর্থের ডিস্টেন্স which is r. Then all of that divided by total mass, which will be ms plus me. This will be my center of mass, which in this case just looks like me times r divided by ms plus me. So সানের সেন্টার থেকে এতটুকু ডিস্টেন্সে, which is let's say this is rcm. এই rcm ডিস্টেন্সকে সেন্টার করে সানও সার্কুলার ট্র্যাকে ঘুরবে, আর্থ সার্কুলার ট্র্যাকে ঘুরবে। But then the thing is, the sun is much more massive than earth. Earth's mass হচ্ছে about 10 to the power 24 kg. r is, okay, so this is me. r is about 10 to the power 15 meters, and ms is about 10 to the power 30 meters, 30 kg. Okay, and if you plug these values in, you'll get that the center of mass actually lies inside the sun's surface. Like the center of mass is inside sun. Sun's center থেকে slightly একটু distance. So যে কারণে দেখা যায়, if this is our sun, এটা হচ্ছে সানের জিওমেট্রিক সেন্টার, সেন্টার অফ মাস হয়ে দাঁড়ায় এটা। সো আমাদের সান হচ্ছে এরকম একটা অরবিটে ঘুরতেছে, এন্ড আর্থ কি করতেছে, আর্থ হচ্ছে এরকম একটা অরবিটে ঘুরতেছে, which looks almost circular because it is going on a circular track, not around sun center, সানের সেন্টার থেকে একটু পাশে, and that deviation is actually very small, যার কারণে most orbits just look circular. But in reality what ends up happening is কোনো একটা স্পেসিফিক অবজেক্টকে ইয়ে করে না, কোনো একটা স্পেসিফিক অবজেক্টকে সার্কেল করে না, they just circle the common center of mass. All right, then we have Kepler's second law. Second law is a bit weird, you guys might think, because second law এর application এই কেসে খুব একটা useful না. In fact, circular case it's almost trivial. So Kepler's second law tells you যে এই যে সার্কুলার ট্র্যাকে যে ঘুরতেছে, এটা ধরো আমার ট্র্যাকের সেন্টার, এন্ড এই হচ্ছে আমার আর্থ। সো ইট জাস্ট টেলস ইউ যে এই সেন্টার আর আর্থের কানেক্টিং লাইন ইকুয়াল টাইমে ইকুয়াল এরিয়া ট্রান্সভার্স করে। So let's say you look at it for 10 hours. Earth moves from here to here. So the area covered by this line is this. Then মনে করো আর্থ এই জায়গায় ছিল, এখান থেকে তুমি 10 দিন দেখলে, 10 ঘন্টা দেখলে, it goes here. এই area and এই area, these two will be the same. For circular tracks, it's very trivial because এই কোণ আর এই angle same হইতে হবে. If these two angles are the same, you clearly have same area since it's a circle. But then it becomes more useful for elliptical cases, which we will not be going into in this class. So এটা নিয়ে আমরা খুব একটা ডিটেইল ডিসকাস করব। The more useful is actually Kepler's third law. Kepler's third law tells you that the period of this motion, আর্থ যে যাচ্ছে সানের চারিদিকে, এটা যে ঘুরছে, ঘুরে যে ব্যাক আসবে, এই ব্যাক আসার যে পর্যায়কাল, that is proportional to radius cubed. আমার যে ট্র্যাক ছিল সেই ট্র্যাকের রেডিয়াসের কিউবের proportional হচ্ছে t square. This one we will prove actually. This is really useful. So let's do it for the sun case first. It's really easy to do with Newton's laws actually. So sun's case, sun is very massive. So sun is almost stationary at the center, and sun to earth distance ধরলাম r, and here is earth moving around. So what is the, like, for let's say earth velocity is v. V velocity জন্য আমার একটা centripetal force থাকা লাগবে. That will be me v squared divided by r. But then where is this force coming from? This is coming from the gravitational force. So this will be equal to g ms me divided by r squared. You cancel out me, you cancel out one r, you get v squared is g ms divided by r. Or okay, it's not exactly done, but then v এর জন্য আমরা আরেকটা ইকুয়েশন বসাইতে পারি। দেখো আমার এটা যদি কনস্ট্যান্ট স্পিডে যাই, দেন যখন ঘুরে টোটাল আবার এখানে ব্যাক আসছে, টোটাল ডিস্টেন্স কভার্ড ইজ 2 pi r, and if the time period is t, then my velocity is 2 pi r divided by t. If we plug this in and square it, you get 4 pi squared r squared divided by t squared is g ms divided by r. T squared ka alada karo, you get t squared is 4 pi squared divided by g ms times r cubed. So this is my formula. This is assuming ms is much larger than me. When did you assume this? When you assumed যে আমাদের sun হচ্ছে stationary, তখন আমরা assume করে নিচ্ছি যে ms, mass of sun, is much greater than earth's mass. Otherwise sun ও move করতো, then we would have a different scenario. সেই scenario একটু পরে আমরা কাজ করব, but this is the case we have when mass of one object is much larger than the other object. And খেয়াল করো, in this equation the mass of the lighter object doesn't appear. me doesn't appear anywhere. Okay, and you can actually try to plug in answer values, and you can see t will be 365 din for earth. For example, mass of the sun is 2 into 10 to the power 30 kg, and g, as we mentioned before, is 6.673 into 10 to the power minus 11 Newton meter square per kg squared. And r, earth to sun distance, if I'm not wrong, should be 1.5 into 10 to the power 11 meters. So if you plug this value in, obviously তুমি t পাবা শুরুতে সেকেন্ডসে, সেই সেকেন্ডস থেকে যদি তুমি দিনে কনভার্ট করো, this should be around 365 days. Which basically tells you, okay, your calculation is at least in the correct order of magnitude, or like around the correct value. So again, this is the equation যেটা দিয়ে you find period of different planets when you know the distance, when you know their orbit. But the condition is what? Condition is mass of the object that is being, like mass of one of the objects is much greater than the other object. Other possible scenario কি হইতে পারে? মনে করো আর্থের চারপাশে স্যাটেলাইট ঘুরতেছে. Usually all of the satellites we use, তাদের তুলনায় আর্থের mass is huge. স্যাটেলাইটের mass কতই হয়? হয়তো like 4000 kg. আর্থের mass কত? আর্থের mass is 610 to the power 24 kg, which is huge. So in those cases, you can use this equation as well, because Earth's mass is much greater than mass of those satellites. However, when you cannot use this equation, is, let's say I tell you there are two stars. These are called binary star systems. এরকম star system universe খুবই common. You have two stars, and for an extreme case, let's set their mass to be equal. Let's say এর mass হচ্ছে m, এর mass ও m, and the distance between them is L. সো এরা যে চলতেছে এদের অরবিটের পিরিয়ড বের করতে হবে। First of all, where is the center of mass? If you use the same equation, you first have to set a coordinate system. In a coordinate system, then you have to find sum of MIRI. For first object, it's m times 0. For second object, it's m times L. So my R will be, this is just ML. My R will be ML divided by net mass, which is 2m, which gives you L over 2, which makes sense. Your center of mass is in the middle point. এই হচ্ছে তোমার মিডল পয়েন্ট। নাও ইট মিনস যে এই মিডল পয়েন্টকে সেন্টার করে এখন তোমার দুইটা অবজেক্টে সার্কুলার ট্র্যাকে ঘুরবে, which means তোমার অবজেক্টগুলো এরকম ট্র্যাকে ঘুরবে। They will move around in the same circle, but exactly in the opposite direction. So এ যদি এদিকে মুভ করে, এদিকে মুভ করবে। So the radius of the circle will be L over 2. যেহেতু এরা সেম সার্কেলে মুভ করতেছে, এদের ভেলোসিটি সেম হইতে হবে। Then you just keep doing the same thing. The centripetal force in this case on one object, a object এর উপর ধরলাম, it will be m v squared divided by r. What is r? R is L over 2. That is equal to the gravitational force. Gravitational force কত? Gravitational force is g m into m, which is m squared, divided by L squared. Remember, the distance between the two objects is L. Gravity te you use the distance between two objects. This is the distance between two objects. This is the radius of the orbit. These two in general are not the same r. Just as in this case. এই কেসে এর নিচে এটা আসছে L, which is the distance between two objects. এর নিচে আসছে L over 2, which is radius of the orbits. They are not the same. If you cancel m and m out, and similarly v এর জন্য কি লিখবো? V এর জন্য you will write 2 pi r, which is L over 2 divided by t. So that gives you pi L over t for v. So if you plug everything in, you get pi squared L squared over t squared is equal to gm over 2L. Right? This 2 goes up, this comes down, yes. Or you get t squared is pi squared divided by gm times 2 pi squared actually. Yes, 2 pi squared by gm times L cube, which looks a lot different from the other equation, but it's still t squared is proportional to L cube. T squared is proportional to the distance between two objects. That is always true. So your time period will always be proportional to the distance between two objects. এখানে distance L, এখানে distance R. So t square is proportional to L cubed. That is correct. But the proportionality constant, that has changed. In fact, if you try to find the general case, which I don't think I have time to do now, you will find that the general formula is this. Actually, I will keep it as an exercise for you guys. So your exercise is to prove this. This is the general case. General case কখন? You have two objects of mass m1 and m2. m1, m2. এদের মধ্যে distance হচ্ছে L. And then এরা একজন আরেকজনের রেসপেক্টে সার্কুলার ট্র্যাকে ঘুরতেছে। একজন আরেকজনের রেসপেক্ট না, বেসিক্যালি এদের সেন্টার অফ মাসের রেসপেক্টে সার্কুলার ট্র্যাকে ঘুরতেছে। So you don't assume m1 is larger, m2 is larger or anything. I will help you guys in that. I will help you guys with finding the exact trajectory, how the trajectories will look like. First, we try to find the center of mass. এখানে coordinate center নিলাম. So I have m1 times 0 plus m2 times L divided by m1 plus m2. This is my center of mass. So if I redraw the diagram, I have m1 here, I have m2 here, and my center of mass is somewhere around here. where this distance is m2L divided by m1 plus m2. And you can just find this distance, which will be L minus this value. That should come out to be m1L divided by m1 plus m2. So this is my center of mass. This is center of mass. Now, in center of mass respective, both objects circular track এ ঘুরবে. So m1 at track would look something like this. Which is a circle of radius m2L divided by m1 plus m2. So this is for m1. What about m2? M2's track would look something like this. যার রেডিয়াস হবে m1L divided by m1 plus m2. So they are still circular tracks, but of different radius. Now you might think, okay, then আমি কোনটার time period হিসাব করব? দুইটা time period actually same হতে হবে, because remember my center of mass cannot change. So আমার m1 যখন ঘুরে আবার আগের জায়গায় ব্যাক আসবে, m2 ও ঘুরে আগের জায়গায় ব্যাক আসা লাগবে। So আমার m1 এর টাইম পিরিয়ড যদি t হয়, m2 এর টাইম পিরিয়ড t হইতে হবে। They will have different velocities because they have different distances to cover. এটাকে যদি আমি r1 লিখি, এটাকে যদি r2 লিখি, তাহলে প্রথমটার ভেলোসিটি হবে v1 হবে হচ্ছে v1 হবে হচ্ছে 2 pi r1 by t, v2 হবে হচ্ছে 2 pi r2 by t. So they will have different velocities, but the time period will be the same. কেন? Because the moment m1 comes back here, m2 should also come back to the original position. So that time period same হওয়া লাগবে. So you pick either of the objects, you can try to find for both, and you will find that if you either one you use, you'll get the same equation for t. So you basically do again the same thing. Let's do on m1. m1 এর উপর হবে হচ্ছে m1 v1 squared divided by r1 is equal to g m1 m2 divided by l squared. Remember, our গ্র্যাভিটিতে নিচে যাবে হচ্ছে total distance, radius এর নিচে যাবে হচ্ছে radius. If we plug in the value of the radius এখানে, তাহলে r1 এর ভ্যালু বসাই দিলে you get m2l, উপরে পাবা m1 plus m2. And then actually let's keep it like this because আমার v1 এর মধ্যে একটা r1 আছে. So let's cancel out the m1 first. v1 যদি আমি বসাই দিই, I get 4 pi squared r1 squared, but একটা r1 cancel out হয়ে যায়, so I'll have 4 pi squared r1 divided by t squared is equal to gm2 divided by l squared. I'll just complete the derivation since we're almost there already. 4 pi squared divided by t squared times r1, which is m2l divided by m1 plus m2 is equal to gm2 divided by l squared. You cancel out m2, you cancel out l here, make it l cubed. Then if you just isolate t squared, you get 4 pi squared divided by g m1 plus m2 times l cubed. This is the general formula for circular orbits. Circular orbit na hole ki, we don't get into that because that is beyond our syllabus for this class. And you can see, you just need to remember this actually, because let's say m1 is much larger than m2. In that case, my m1 plus m2 basically becomes m1. Then we go back to the first equation. So এখানে if m1 is much larger than m2, m1 plus m2 becomes m1 because m2 is very small. In that case, this equation just corresponds to this. Then if m1 is equal to m2, you get m1 plus m2 is equal to 2m1. If you plug that in, you get back this equation. So basically, this is the only equation you need to remember for circular orbits, obviously. So with this, you can basically find the time period of satellites for different planets, of different astronomical objects, as long as you know that the orbit they're going through is circular. If it's elliptical orbits, you need to make some adjustments. But again, we won't be getting into that today. Okay, so that's kind of it. To summarize the orbit part, gravity under it, you can have 4 types of orbits. But then we are only concerned with bounded orbits. Jegula don't go to infinity. For bounded orbits, you can have circular orbits or elliptical orbits. Then we are only concerned with circular orbits in this course. So circular orbits, the key idea is you need a centripetal force, which is given by mv squared by r, and that is supplied by gravity, gmm by l squared. So what you do, you first find how the orbits are going to be. Orbits are how? Orbits are usually so that both of your orbits are circling the center of mass, the common center of mass. So once you have the radius of like circulations and stuff, you find the total gravitational force, set that equal to the gravitation to the centripetal force, and solve for whatever quantity you need. And that usually gives you a special form of Kepler's third law. Okay, so that's about it. If you have any questions, feel free to ask, and I will see you in the next class.